The Medical Future of Neurotechnology. Hosted by me, Ralph Clayton. This episode is not about mind uploading. It is not about escaping the body. It is not about copying a human soul into a machine. That is the science fiction version of the story. The real trend is quieter, more clinical, more difficult, and in many ways, more important. The real trend is medical neurotechnology. Brain-computer interfaces, closed-loop neurostimulation, neuroprosthetics, brain organoids, digital twins, neuromorphic twins, systems that do not try to replace the human brain, but try to listen to it, understand it, support it, repair its broken loops, and, when possible, restore a lost function. This is VTM Podcast. I'm Ralph Clayton, and today, in episode 14, we are talking about one of the most misunderstood frontiers in science, neurotechnology, not as fantasy, not as hype, but as medicine. For years, the public imagination has been captured by extreme ideas. Uploading a mind, merging humans with artificial intelligence, building a brain inside a computer, creating immortal digital consciousness. Those ideas are dramatic. They make headlines. They make movies. They make people either excited or terrified. But they are not where the most serious near-term progress is happening. The real movement is happening in hospitals, in rehabilitation labs, in neurosurgery units, in computational neuroscience, in prosthetics clinics, in epilepsy treatment, in Parkinson's disease, in spinal cord injury, in stroke recovery, in depression research, in brain modeling, in devices that can read neural signals, and in systems that can respond to those signals in real time. The key word is not immortality. The key word is restoration. Restoring movement, restoring communication, restoring sensation, restoring adaptive control, restoring stability to a nervous system that has fallen into pathological rhythm. The nervous system is electrical, chemical, biological, dynamic. It is not a hard drive. It is not a file cabinet. It is not a simple computer waiting to be copied. It is a living, changing, embodied system. It learns, it adapts, it compensates, it rewires, it breaks, it heals, it resists. And modern neurotechnology is beginning to work with that complexity instead of pretending it does not exist. That is why the future of the field is not a fantasy of leaving the brain behind. It is the much harder task of building technologies that can cooperate with the brain while the brain is still alive, changing, still human. Let's begin with brain-computer interfaces. A brain-computer interface, or BCI, is exactly what the name suggests. It is a system that creates a pathway between neural activity and an external device. A person thinks about moving a cursor. The system detects patterns in neural activity The computer translates those patterns into commands. The cursor moves. A person with paralysis imagines moving a hand. The system decodes intention. A robotic arm responds. A person who cannot speak attempts to form words. The system reads activity related to speech. A machine generates text or synthetic speech. That is the basic promise. A bridge between neural intention and external action. For someone with a healthy body, moving is almost invisible. You decide to reach for a glass, your arm moves. You decide to speak, words come out. You decide to walk, your body carries you. But for a person with paralysis, stroke damage, AS, spinal cord injury, or locked in syndrome, intention may remain, while the pathway to action is broken. The person may still want to move, still want to speak, still want to reach, still want to interact, but the signal cannot reach the muscles. A BCI tries to build a new pathway, not by curing everything at once, not by magically restoring the body, but by reading the signal where it still exists and routing it through technology. This is already profound, but the field is moving beyond one-way decoding. The old model was simple. Brain sends signal, computer reads signal. Device acts, that is open loop control. But the brain does not naturally operate in open loops. The brain acts and receives feedback. You move your hand, you feel pressure, you adjust grip, you speak, you hear your own voice, you correct tone, you walk. Your body reports balance, weight, tension, and motion. The nervous system is built from loops, perception and action, prediction and correction, command and feedback. That is why the next major frontier is closed-loop neurotechnology. A closed-loop system does not merely read from the brain. It reads, interprets, acts, measures the effect, and adjusts. In medicine, this can mean a device that detects abnormal neural activity and delivers stimulation only when needed. It can mean a neuroprosthetic limb that not only moves, but returns sensory information. It can mean a brain-computer interface that adapts to the patient's changing neural signals. It can mean a stimulation system that responds to tremor, mood state, seizure patterns, or movement intention in real time. The difference is crucial. An open loop system says, here is the same stimulation again and again. A closed loop system says, what is happening now? What does this patient need now? How should the system respond now? That shift changes the entire philosophy of treatment. Because the brain is not static. A patient is not static. Symptoms are not static. Neural signals drift. Medication levels change. Sleep changes. Stress changes. Plasticity changes the map. The disease itself changes over time. So the device must adapt. This is where artificial intelligence enters the story. AI Enabled medical neurotechnology is not simply about decoding more signals. It is about making sense of signals that are noisy, personal, variable, and constantly changing. Every brain is different. Every injury is different. Every disease state has its own rhythm. A stimulation protocol that helps one person may not help another. A decoder trained on one day may perform worse the next day. A prosthetic interface may need recalibration. A brain state may look different depending on fatigue, medication, attention, or emotion. AI can help by learning patterns across time, by identifying useful features in neural data, by adapting decoders, by optimizing stimulation, by finding personalized settings, by making the system more responsive. But there is a serious challenge here. The more complex the AI becomes, the harder it can be to explain. And in medicine, explanation matters. A patient may ask, why did the device stimulate at that moment? A clinician may ask, why did the model change the setting? A regulator may ask, how do we know this system is safe? A researcher may ask, what did the model actually learn? If the answer is only, the model decided, that is not enough. Medical neurotechnology needs trust. And trust requires transparency. Not perfect transparency in every mathematical detail, but enough explainability for clinicians to understand risk. Enough traceability for researchers to reproduce results. Enough control for patients to know what is being done to their own nervous system. Enough humility to know when the model should not act. This is one of the great tensions of 2026 neurotechnology. The systems are becoming more intelligent, but medicine demands that intelligence remain accountable. Now, closed-loop neurostimulation deserves special attention, because it may become one of the most practical near-term medical uses of advanced neurotechnology. Neurostimulation is not new. Doctors have used electrical stimulation in the nervous system for years. Deep brain stimulation can help some patients with Parkinson's disease and other movement disorders. Responsive neurostimulation can help some patients with epilepsy. Spinal cord stimulation can help with certain forms of chronic pain. Other forms of stimulation are being explored for depression, obsessive, compulsive disorder, stroke rehabilitation, memory disorders, and more. The basic idea is that abnormal patterns in the nervous system can sometimes be disrupted, corrected, or modulated by carefully delivered electrical stimulation. But traditional stimulation can be blunt. A device may stimulate according to a preset schedule, or at a fixed intensity, or in a fixed anatomical target, even when the patient's brain state changes. Closed-loop stimulation tries to make therapy more precise. It listens before it acts. It detects a signal, a seizure-related pattern, a tremor, related rhythm, a marker of impaired movement, a neural signature of a pathological state. Then it responds, not constantly, not blindly, but contingently. The stimulation becomes part of a feedback system. This is powerful because the timing of stimulation can matter. The brain is rhythmic. Networks oscillate. Neurons fire in patterns. Plasticity depends on timing. A signal delivered at the wrong time may do little. A signal delivered at the right time may help reshape the loop. In rehabilitation, this is especially important. After stroke or injury, recovery depends partly on neuroplasticity. The brain must relearn. The body must remap. Surviving pathways must strengthen. New strategies must emerge. A closed loop BCI for rehabilitation can connect intention, feedback, and movement in a timed loop. The patient tries to move. The system detects the attempt. A device assists the movement. The patient sees or feels the result. The brain receives feedback that the intended action occurred. Over time, that loop may support plasticity. It is not magic. It is training, but technologically amplified training. A loop that tries to align neural intention with sensory feedback and physical outcome. That is why closed loop neurotechnology is so different from the fantasy of mind uploading. It does not treat the brain as information to be extracted. It treats the brain as a living system to be engaged. The goal is not to abandon biology. The goal is to guide biology. Now let's talk about neuroprosthetics. A prosthetic limb used to be mostly mechanical, a replacement structure, a hook, a hand, a leg, a tool that restored some physical capability, but often without natural sensation or fine control. Modern neuroprosthetics are becoming far more ambitious. They aim to connect the prosthetic to the nervous system, to decode motor intention, to provide sensory feedback, to restore touch, to allow more natural control, to make an artificial limb feel less like an external tool and more like part of the body's action system. This is not easy. The nervous system does not speak in simple commands. It does not send a clean message that says, "Move finger 3 at exactly this speed." Neural signals are distributed, noisy, contextual, adaptive. A useful neuroprosthetic interface must interpret signals from nerves, muscles, brain areas, or implanted electrodes. Then, it must translate those signals into device control. Then it must return useful feedback, texture, position, movement, force, temperature someday, perhaps, pain, ideally not. The hard problem is not only movement, it is embodiment. Can the person learn to control the prosthetic naturally? Can the brain incorporate it into its body map? Can feedback feel meaningful instead of confusing? Can the system remain stable over months and years? Can it adapt as the person changes? This is where personalized modeling becomes critical. A neuroprosthetic interface may not be optimal out of the box. It has to be tuned. Where should electrodes be placed? What stimulation pattern creates a useful sensation? What control algorithm matches this person's neural signals? What settings reduce fatigue? What design supports learning? In 2026, one of the important emerging ideas is the use of digital twins and computational models to optimize neuroprosthetic interfaces. A digital twin, in this context, is not a copy of a person's mind. That is important. It is a model of the relevant biological and technological system. For example, a model of how electrical stimulation interacts with nerves, or how a prosthetic interface sends signals into tissue, or how a patient-specific anatomy affects current flow, or how different stimulation patterns may produce different perceptual effects. The goal is practical. Predict before cutting. Simulate before implanting. Personalize before trial and error becomes exhausting. A digital twin can help researchers explore possible designs in silico before testing them in a patient. It can reduce unnecessary experimentation. It can help tailor stimulation to individual anatomy. It can guide safer and more efficient neuroprosthetic development. Again, this is not science fiction immortality. It is clinical engineering. The twin is not the person. The twin is a tool, a model that helps doctors and engineers make better choices. Now there is a related but distinct concept that may become very important. Neuromorphic twins. Neuromorphic engineering is inspired by the nervous system. Instead of using conventional computing architectures that process information in a sequential, energy-hungry way, neuromorphic systems often use event-driven designs, spiking circuits, and architectures that resemble certain principles of neural computation. Why does this matter for neurotechnology? Because the brain is not a standard computer. It is massively parallel, event-driven, adaptive, energy-efficient, distributed, time-sensitive. If you want to build a device that interacts with the brain in real time, conventional computing may not always be ideal. Latency matters. Power matters. Adaptation matters. Implantable devices cannot simply run like giant data centers. They must be small, safe, efficient, reliable, and responsive. Neuromorphic systems may offer a better match for certain closed-loop neural interfaces. They can process signals in a way that is closer to the timing and event structure of biological neural activity. They may help create devices that respond faster, consume less power, and adapt more naturally to neural dynamics. A neuromorphic twin can be understood as a biologically inspired computational counterpart that helps model, emulate, or interact with neural circuits. Not a full brain copy. Not a digital person. A functional, dynamic model for treatment, testing, prediction, or control. This idea is especially interesting for brain disorders. Many neurological and psychiatric conditions are disorders of dynamics. The problem is not always a single broken part. It may be a network stuck in the wrong rhythm, a circuit that cannot regulate itself, a system that overfires, a loop that loses balance, a timing problem, a coordination problem, a state transition problem. Neuromorphic twins could help scientists understand these dynamical patterns. They could support personalized electroceutical therapies. They could help design stimulation strategies that are flexible instead of rigid. They could become part of systems that learn with the patient. But the field must be careful. A model of brain dynamics is still a model, and brain disorders are deeply personal. Symptoms are lived experiences. A depression score is not a soul. A seizure pattern is not a full life. A motor deficit is not the whole person. The danger in advanced neurotechnology is reduction. Reducing the person to signals. Reducing suffering to data. Reducing treatment to optimization. Good neurotechnology must resist that. It must remember that the patient is not the device's environment. The patient is the reason the device exists. Now we need to talk about brain organoids. Brain organoids are small, lab-grown, three-dimensional structures made from stem cells that develop some features resembling early brain tissue. They are not tiny conscious brains. They are not miniature people. They are models, imperfect models, but potentially powerful ones. They can help researchers study human neurodevelopment, disease mechanisms, drug responses, genetic disorders, cell interactions, network formation, and biological processes that are difficult to study directly in a living human brain. This matters because animal models, while essential, do not always capture human brain biology. The human brain has unique developmental timing, cell types, architecture, and vulnerability. Organoids may provide a more human, relevant platform for certain kinds of research. In neurotechnology, organoids sit at an interesting crossroads. They can support disease modeling. They can help test drugs. They can help explore how neural tissue grows and organizes. They may contribute to neural tissue engineering. They may one day help researchers study how biological neural systems interact with artificial interfaces. But organoids also raise ethical questions. As they become more complex, what limits should exist? How do we define morally relevant neural activity? When does a model remain a model? What kinds of experiments are acceptable? How should researchers monitor complexity? How do we communicate this to the public without causing either panic or false excitement. The responsible answer is not to sensationalize. Most organoids today are far from anything like a conscious brain. They lack the full architecture, body, sensory experience, blood supply, developmental environment, and integrated systems of an actual human brain. But the ethical questions are real, because the field is advancing, and science must govern emerging possibilities before they become emergencies. This is why 2026 neurotechnology is not only a technical frontier, it is a moral frontier. BCAs raise questions about agency. Closed-loop stimulation raises questions about control. Neuroprosthetics raise questions about identity and embodiment. Digital twins raise questions about data and representation. Neuromorphic systems raise questions about autonomy and medical decision-making. Organoids raise questions about biological models and moral boundaries. The future of neurotechnology will be decided not only by what we can build, but by what we can justify. Now, let's return to the biggest public misconception: mind uploading. The idea is emotionally powerful because it touches death. It touches identity. It touches memory. It touches the fear that the self may vanish. It touches the dream that consciousness might be preserved like software. But from a scientific point of view, mind uploading is not the practical center of neurotechnology. The brain is not merely its wiring diagram. It is not only synaptic connections. It is not only electrical spikes. It is also chemistry. Glia, blood flow, body feedback, immune signaling development, experience, plasticity, embodiment, a living history. Even if one could map every neuron and every synapse, that would not automatically capture consciousness, identity, or lived subjectivity. And we are nowhere near doing even that for a living human brain at full functional resolution. So, when people reduce neurotechnology to uploading, they miss what is actually happening. The field is not learning how to escape the body. It is learning how deeply the brain depends on the body. A brain-computer interface works because intention remains embodied. A neuroprosthetic works better when the body can incorporate feedback. Closed-loop stimulation works because timing and state matter. Rehabilitation works because the nervous system can adapt through practice. Organoids matter because biology matters. Digital twins matter because individual anatomy and dynamics matter. The real lesson of modern neurotechnology is not that the brain is easy to digitize. It is that the brain is more dynamic, more personal, and more biologically situated than simplistic computer metaphors ever allowed. That is why the medical path is so important. It begins with suffering. A person who cannot move. A person who cannot speak. A person whose seizures resist medication, a person whose tremor makes daily life difficult, a person with chronic pain, a person recovering after stroke, a person learning to use a prosthetic limb, a person whose nervous system needs help finding a more stable rhythm. Medical neurotechnology is built around these human problems, not around immortality, not around spectacle, around function, dignity, communication, independence, relief, and sometimes small gains that mean everything. A cursor moving across a screen, a word spoken by a synthetic voice, a hand closing around a cup, a sensation of touch returning through an artificial limb, a seizure interrupted before it spreads, a tremor reduced enough for someone to write their name, a rehabilitation loop that helps the brain relearn movement. These are not small miracles to the people living them. They are the real frontier. Now, the role of AI in all of this is growing. AI can improve decoding. It can support adaptive stimulation. It can help personalize prosthetic feedback. It can analyze complex neural data. It can help build patient-specific models. It can support digital twins. It can help closed-loop systems respond to changing brain states. It can make interfaces more usable. But AI must be constrained by medicine. A consumer AI tool can be wrong and annoying. A medical neurotechnology system can be wrong and dangerous. So the standards must be higher. Safety, validation, explainability, clinical oversight, patient consent, cybersecurity, data protection, device reliability, long-term monitoring, and the ability to turn the system off. That last point matters. When technology interacts directly with the nervous system, control is not optional. A patient must not become a passive object inside an automated loop. The loop must serve the person. The person must retain agency. This means consent cannot be a one-time signature. It must be an ongoing relationship. The patient should understand what the system does, what data it collects, what decisions it makes, what risks exist, who can access the data, how the device is updated, what happens if the company fails, what happens if the model changes, what happens if the patient wants the device removed or disabled. Neurotechnology enters intimate territory: speech, sensation, memory, identity. That intimacy requires stronger ethics than ordinary software. It also requires better language. We should be careful with metaphors. A BCI is not telepathy. A neural decoder is not reading the soul. A digital twin is not a duplicate person. A brain organoid is not a little human in a dish. A neuromorphic device is not a brain. Bad metaphors create bad expectations. Bad expectations create hype, fear, exploitation, and disappointment. Good language helps the public understand what is truly possible. and what is not. So here is the cleanest way to frame the trend. The next wave of neurotechnology is about closed loops and personalization. Closed loops because the brain functions through feedback. Personalization because every nervous system is different. A future medical neurotechnology system may listen to a patient's neural state. Compare it to a personalized model. Deliver stimulation or assistance. Observe the response. Adjust in real time and learn over weeks, months, or years. That is the architecture. Sense, model, act, adapt. The same architecture appears across the field. In BCs, in adaptive neurostimulation, in neuroprosthetics, in rehabilitation, in digital twins, in neuromorphic systems, in AI, assisted clinical decision support. The whole field is moving from static devices to adaptive systems. From one-size-fits-all settings to patient-specific tuning. From open loop output to closed loop feedback. From mechanical replacement to biological cooperation. This is why neurotechnology is becoming one of the major scientific trends of 2026. Not because it has solved the brain. It has not. Not because mind uploading is around the corner. It is not. But because the field is becoming mature enough to focus on real clinical architectures, systems that can be tested, improved, regulated, personalized, and integrated into medical care. There is still a long road ahead. Many devices remain experimental. Many interfaces are invasive. Many algorithms are fragile. Many patients will not benefit equally. Some systems will fail. Some companies will overpromise. Some headlines will exaggerate. Some ethical debates will become heated. And the brain will continue to humble everyone who tries to simplify it. But progress is real. The direction is real. The need is real. And the human stakes are enormous. Now let's imagine the clinical future if this path continues. A person has a stroke. Instead of receiving only generic rehabilitation, they receive a personalized neurohabilitation plan. Their movement attempts are decoded. Their muscle activity is measured. Their brain state is tracked. A closed-loop system times stimulation and feedback to support plasticity. A digital model helps clinicians understand which interventions are working. The therapy adapts. Day by day, a person with Parkinson's disease receives adaptive stimulation. The device does not simply stimulate at a fixed level all day. It monitors relevant neural rhythms. It adjusts stimulation based on state. It reduces symptoms while minimizing side effects. The system learns the patient's patterns. The clinician remains in control. The patient remains informed. A person with limb loss receives a neuroprosthetic arm. The arm does not only move. It returns touch. The interface is personalized to their nerves and perception. A model helps tune stimulation patterns. Over time, the patient learns the device, and the device adapts to the patient. Control becomes smoother. Feedback becomes more useful. Embodiment becomes more possible. A person with epilepsy has a responsive system that detects dangerous patterns before they fully develop. It stimulates only when needed. It records data that helps clinicians adjust treatment. It reduces seizure burden. It does not cure every case. But for some patients, it changes daily life. A person who cannot speak uses a speech BCI. The system decodes attempted speech. AI helps translate neural patterns into words. The voice output becomes faster, more natural, more personal. Communication returns. Not perfectly. Not for everyone. But enough to restore social presence. That is the point. Presence. The ability to act in the world. To communicate. To touch. To move. To participate. To regain some measure of control. The greatest promise of neurotechnology is not superhuman enhancement. It is returned agency. This is why the field deserves seriousness. It is not a toy. It is not a spectacle. It is not a shortcut to immortality. It is a medical frontier built around fragile human needs. But seriousness also means asking difficult questions. Who gets access? Will these technologies be available only to wealthy patients? Will insurance cover them? Will public health systems support them? Will patients in poorer countries be excluded? Will proprietary devices lock people into corporate ecosystems? Who owns neural data? Can neural data be supponeed? Can it be sold? Can it be used for advertising? Can employers or insurers demand access? Can a hacked device harm a patient? Can a software update change how someone moves, speaks, or feels? These questions sound dramatic, but they are practical. Once the nervous system becomes connected to software, cybersecurity becomes medicine. Privacy becomes medicine. Device governance becomes medicine. Software updates become medicine. Data rights become medicine. This is why neurotechnology cannot be governed like ordinary consumer electronics. A phone can be replaced. A neural implant is different. A wearable stimulator that affects mood, sleep, pain, or attention is different. A prosthetic limb integrated into body representation is different. A closed, loop brain system is different. The regulatory and ethical frameworks must match the intimacy of the technology. And yet, fear should not paralyze the field. The risks are real. But so is the suffering these systems may relieve. The right response is not rejection. It is responsible development. Strong clinical evidence. Transparent communication. Patient-centered design. Equitable access. Explainable AI where possible. Human oversight where necessary. Security by design. Clear limits on data use. And a culture that values dignity over spectacle. The best neurotechnology will not be the one that makes the loudest claim. It will be the one that works reliably for real patients in real lives. There is also an important spectrum here. Some neurotechnology is invasive. It requires electrodes placed inside the skull, or on the surface of the brain, or near nerves, or inside the spinal system. Invasive systems can capture richer signals and deliver more targeted stimulation, but they also carry surgical risk, infection risk, hardware risk, long-term maintenance questions, and deep ethical responsibility. Other neurotechnology is non-invasive. It uses EEG, wearables, magnetic stimulation, ultrasound, electrical stimulation through the skin, motion sensors, eye tracking, muscle signals, voice signals, behavioral data. Non-invasive systems are usually safer and easier to deploy, but they often have weaker signals, lower resolution, more noise, and less precise control. The future will not be one side winning completely. It will be a spectrum. For severe paralysis, invasive BCAs may be justified. For rehabilitation, hybrid systems may combine EEG, muscle signals, robotics, and feedback. For sleep, pain, tremor, or mood-related applications, wearable or minimally invasive systems may become more common. For prosthetics, interfaces may connect to muscles, peripheral nerves, implanted electrodes, or external sensors. The clinical question is always the same. How much intervention is justified by the need? How much risk is acceptable for the benefit? How much precision is required? How much can be achieved without surgery? A responsible field does not ask only what is technically impressive. It asks what is medically proportionate. That word matters. Proportionate. The most advanced technology is not always the best treatment. Sometimes the best system is the one that is simpler, safer, cheaper, easier to maintain, and good enough to restore function. Neurotechnology must remember that patients do not live inside research papers. They live inside daily routines, homes, families, work, pain, fatigue, hope, appointments, insurance forms, skin irritation, software glitches, fear, adaptation. A technology that works beautifully in a lab but fails in daily life is not finished. The next phase of the field must therefore be practical. Long-term usability, comfort, training, maintenance, clinical workflow, cost, reliability, support, and the emotional experience of depending on a device that interacts with the nervous system. Because restoration is not only engineering, it is life after engineering. Now, before we close, I want to offer a simple framework for understanding this whole trend. Think of neurotechnology in 5 layers. First, sensing. Can we measure meaningful neural or physiological signals? Second, decoding. Can we interpret those signals in a way that connects to intention, state, symptom, or function? Third, modeling. Can we build a useful representation of the patient, the disease, the interface, or the therapy? Fourth, intervention. Can we stimulate, assist, move, communicate, or guide the system in a beneficial way? Fifth, adaptation. Can the whole loop learn over time while remaining safe, explainable, and under human control? The future belongs to systems that can connect all 5 layers: sense, decode, model, intervene, adapt. That is the medical neurotechnology stack. And when AI, neuromorphic computing, robotics, prosthetics, organoid research, and clinical neuroscience converge around that stack, the field begins to change. Not into a fantasy of digital immortality, into a serious medicine of nervous system repair. That is the story of 2026. The hype cycle wants us to ask, when will we upload the mind? The real science asks better questions. Can we help a person speak again? Can we reduce seizures? Can we restore touch? Can we improve rehabilitation? Can we personalize stimulation? Can we model a patient's neural interface before surgery? Can we build devices that adapt without stealing agency? Can we treat the nervous system as living, dynamic, and deeply individual? Those are better questions. More human questions. More useful questions. And much closer to the actual frontier. The brain is not a file. The mind is not a simple program. The person is not a dataset. The future of neurotechnology should begin there, with humility, with precision, with respect, and with the understanding that the highest goal is not to escape being human. It is to help human beings more fully when the nervous system has failed them. That is the promise. Not immortality in a server, not consciousness copied into code, but a hand that moves, a voice that returns, a seizure that stops, a tremor that quiets, a body that learns again, a patient who gains back one more piece of the world. And in medicine, one piece of the world can be everything. This has been VTM Podcast, Episode 14. I'm Ralph Clayton. Thank you for listening. Until next time, keep questioning the future before it becomes the present.